morning and welcome to my talk. I'm Enrico Brugnolotto and today I will be talking to you about our analysis carried out with electron microscopy and energy dispersive X-ray spectroscopy of indium gallium arsenide indium phosphide heterostructures grown using TASE in horizontal nanowires. TASE stands for Template Assisted Selective Epitaxy, which is a monolithical integration method that allows us to grow 3,5 directly from a silicon substrate. TASE process begins with the definition of our nanostructures on a silicon layer, which is then covered by silicon oxide, which will form the template, which when open allows us to etch back the silicon, leaving only a silicon seed, from which then we can grow the 3,5 material using metal organic vapor deposition. TASE has many advantages. It is CMOS compatible, allows for nanometer precise integration of horizontal nanostructures of flexible geometries, and also allows us to have high defect control. In this study, the authors were able to integrate a PAN photodetector made of 3,5 material directly on silicon using TASE. After they grew the device, they stripped the template oxide to contact the P and N side of the photodetector to conduct photocurrent measurements. TASE can also be used to grow 3,5 material from a 3,5 substrate. In this other study, the authors grew indium phosphide indium gallium arsenide heterointerfaces from an indium phosphide seed. In our group, we also managed to integrate 3,5 photodetectors on silicon with TASE. The I region of the device was made of indium gallium arsenide, while the P and N region were made of indium phosphide. The authors indicated good performance for this kind of device, and also suggested that with a better control of the heterointerfaces and with the possible introduction of a 3,5 type II superlattice in the I region, this performance could be improved even further. But can we achieve the necessary level of interface control to grow such thin 3,5 material layers? This is what we set out to find out. Our TASE structures are grown with the MOCVD method, which stands for metal organic chemical vapor deposition. In our MOCVD setup, a hydrogen flow transports the various precursors to the reaction chamber. Here, they are deposited on the substrate, which lays on a rotating and heated plate. The growth recipe is then composed of different steps that happens at different temperature and are marked by different precursor flows. To begin with, first oxygen desorption step takes place in arsenic atmosphere at 750 degrees. Then the actual growth process begins at 580 degrees. The first layer to be deposited is an indium gallium arsenide nucleation layer, followed by a first indium phosphide barrier, and then the actual 3,5 superlattice of indium gallium arsenide and indium phosphide can be deposited. The result of this growth process is on the top right, a silicon seed on the left of the image, from which a 3,5 wire grows here in lighter gray. To the right of the wire, you can also see the empty template and the template opening through which the precursor entered the template to reach the growth front. We then select one of the wires for analysis. To prepare the sample, we perform a fib cut to create an electron transparent lamella, which we can then image using our atomic resolution scanning transmission electron microscope. This tool allows us to conduct both compositional and structural analysis of our samples. We began our nanowire growth studies by employing a simple growth recipe. This was to better understand the mechanisms behind each growth step. This is why in our first experiment, we only grew an indium gallium arsenide nucleation layer, followed by an indium phosphide barrier layer. From the resulting nanowire, we then took this electron microscopy image and these EDS maps, which both already highlight a peculiarity in the evolution of the growth front. In fact, during the growth of the indium gallium arsenide layer, the growth front presents multiple facets, top 110 facets, and a single 111 facet at the bottom. However, during the growth of the indium phosphide layer, the material grows quickly in the 110 direction, extinguishing the corresponding facets, and stabilizing, as a result, a single facet for the growth front, the 111 facet. We then proceeded to add, or try to add, thin layer of indium gallium arsenide and indium phosphide to the right of our previously grown structure here. We were only partially successful in doing that, as we grew a 6 nanometer 3-phosphide layer sandwiched between two 3 arsenide layers. This heterostructure shows good definition on the 5-component side, as you can see in the zoom in of the 5-component EDS map here in full. If you however zoom in on the 3-component EDS map, we cannot identify any sharp composition gradient, and the entire region seems to suffer from extensive alloying. If we then analyze the area to the right of the 3-phosphide heterostructure that we saw before, we can see that the indium concentration, here in red, appears to onset after the phosphide layer has stopped growing. Here you can see the phosphide concentration in blue. This becomes especially apparent if we highlight both of the concentration profiles in both maps and then superimpose them. Seems that there is a certain integration delay for the 3-component. We have then identified a few building blocks to base our next growth recipe on. These are the growth front stabilization created by the indium phosphide layer, and the possibility to create thin heterostructures, so far with good 5-element definition. However, we still need to address a couple of issues that we have also identified, which are the 3-component alloying and the integration delay for the 3-component. To formulate this new growth recipe, we must then find the underlying cause of both of these issues and try to solve it. Both of the issues that we identified involve the 3rd group component. When looking for a cause, we then focused on finding what is remarkably different in the mechanisms involving the 3rd component from the ones involving the 5th component. We drew our attention to the diffusion mechanisms inside the template oxide. In fact, both 3 and 5 components diffuse through the vapor phase. However, an extra diffusion route is available to the 3 atoms that are adsorbed on top of the silicon oxide template walls. If this surface diffusion mechanism is slower than the vapor phase diffusion one, we would expect then both of these issues to arise. For short recipe steps, both of the 3 components would be reaching the growth front interface at any given time, causing the alloying issues. At the same time, after an indium phosphide growth step, there would be extra indium present in the system and still reaching the growth interface, causing this indium rich area after the phosphide area. In order to allow time for the 3 precursors diffusing on the surface to reach the reaction interface, the growth front, we introduced some buffer steps in the recipe. During these steps, we altered the flow of the 3 components, but maintained a 5-component overpressure to avoid desorption of the 5-component from the growth front. At the same time, we also adjusted the step time, made the indium gallium arsenide well deposition step time shorter and the indium phosphide barrier step time longer in order to achieve the desired layer thicknesses and the desired stacking. We also kept some process parameters constant to keep benefiting from the good building blocks that we identified in the first experiments, which were the growth front stabilization during the indium phosphide step and the possibility for sharp interfaces in thin layers. These constant process parameters were the process temperature and the 5:3 ratio. The effect of the new growth recipe on the growth are already evident from this lamella cutout of one of the new nanowires grown with this new recipe. Already from the electron image, the channeling contrast reveals two indium gallium arsenide wells between indium phosphide barrier layers. The conclusions that we drew from the channeling contrast in the electron microscopy image are further confirmed by the EDS maps of the 5 and 3 elements. In the 5-element map, we can notice how the arsenide regions are now the thin ones, as opposed to the phosphide regions in the first growth experiments. The interfaces are just as sharp for the 5 elements. However, for the 3 elements, we can notice a marked improvement in the sharpness of the hetero interfaces. Looking at the composition profile through the quantum wells for the 3 element, we can see how at the beginning, before the quantum well onset, the indium is a majority element. Through the first hetero interface, the concentration of indium drops until it reaches about 50% inside the quantum well itself. This is the concentration we were aiming for with the ratios between the 3 precursors during the growth. After the end of the quantum well region, the indium concentration again sharply raises and indium becomes the majority element. If we perform a similar analysis on the 5 element, again, we take a composition profile through the quantum well, we can see how in the indium phosphide layer, as we expect, phosphorus is the majority element. Phosphorus concentration then drops sharply at the quantum well interface, and the arsenic composition shoots up to make arsenic the majority element in the quantum well itself. After the second interface, there is again a sharp drop in arsenic concentration and a sharp rise in phosphorus concentration. This time, however, there seems to be a little bit of lingering right after the interface of some arsenic impurities, which are nonetheless the minority element. In conclusion, we have demonstrated that it is indeed possible to achieve this optimal interface control that would allow us to integrate 3-5 type II superlattices on silicon using TASE, and we have showed one example of such a superlattice. This research will be the basis for further development, especially the introduction of vertical heterointerfaces as opposed to the tilted ones you saw in this presentation will also be one of our future objectives, as well as better layer thickness management. Currently, the heterostructures that you have seen consist of a 15 nanometer wide indium gallium arsenide layer. We would like to thin this layer down to sub 10 nanometer levels. In order to do so with good results, we would then also tackle this lingering of arsenide after the second hetero interface of the quantum well by optimizing the buffer steps. With this, I thank you very much for your attention. I will be welcoming all the questions you may have in the Q&A session later on, or through email, or for those of you who prefer, through LinkedIn. You can connect to my LinkedIn profile using the QR code on the right. Thank you again, and I hope you enjoyed the rest of the conference. Bye.